ch05.7955 page 106 Friday, January 21st, 2005 10:41 am. Chapter 5 Concurrency and Race Conditions. Thus far, we have paid little attention to the problem of concurrency, i.e., what happens when the system tries to do more than one thing at once. The management of concurrency is, however, one of the core problems in operating systems programming. Concurrency-related bugs are some of the easiest to create and some of the hardest to find. Even expert Linux kernel programmers end up creating concurrency-related bugs on occasion. In early Linux kernels, there were relatively few sources of concurrency. Symmetric multiprocessing (SMP) systems were not supported by the kernel, and the only cause of concurrent execution was the servicing of hardware interrupts. That approach offers simplicity, but it no longer works in a world that prizes performance on systems with more processes, and that insists that the system respond to events quickly. In response to the demands of modern hardware and applications, the Linux kernel has evolved to a point where many more things are going on simultaneously. This evolution has resulted in far greater performance and scalability. It has also, however, significantly complicated the task of kernel programming. Device driver programmers must now factor concurrency into their designs from the beginning, and they must have a strong understanding of the facilities provided by the kernel for concurrency management. The purpose of this chapter is to begin the process of creating that understanding. To that end, we introduce facilities that are immediately applied to the skull driver. From Chapter 3, other facilities presented here are not put to use for some time yet. But first, we take a look at what could go wrong with our simple skull driver and how to avoid these potential problems. 106. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly & Associates, Inc. All rights reserved. ch05.7955 page 107 Friday, January 21st, 2005 10:41 am. Pitfalls in Skull. Let us take a quick look at a fragment of the Skull memory management code. Deep down inside the write logic, Skull must decide whether the memory it requires has been allocated yet or not. One piece of the code that handles this task is if dptr to data s_pos opening curly bracket dptr to data s_pos equals kmalic quantum. If dptr to data s_pos go to out closing curly bracket. Suppose for a moment that two processes, we'll call them A and B, are independently attempting to write to the same offset within the same skull device. Each process reaches the if test in the first line of the fragment above at the same time. If the pointer in question is null, each process will decide to allocate memory, and each will assign the resulting pointer to dptr to data s_pos. Since both processes are assigning to the same location, clearly only one of the assignments will prevail. What will happen, of course, is that the process that completes the assignment sequentially will win. If process A assigns first, its assignment will be overwritten by process B. At that point, Skull will forget entirely about the memory that are allocated. It only has a pointer to B's memory. The memory allocated by thus will be dropped and never returned to the system. This sequence of events is a demonstration of a race condition. Race conditions are a result of uncontrolled access to shared data. When the wrong access pattern happens, something unexpected results. For the race condition discussed here, the result is a memory leak. That is bad enough, but race conditions can often lead to system crashes, corrupted data, or security problems as well. Programmers can be tempted to disregard race conditions as extremely low probability events. But in the computing world, 1 in a million events can happen every few seconds, and the consequences can be grave. We will eliminate race conditions from Skull shortly. But first we need to take a more general view of concurrency. Concurrency and its management. In a modern Linux system, there are numerous sources of concurrency and, therefore, possible race conditions. Multiple user space processes are running, and they can access your code in surprising combinations of ways. SMP systems can be executing your code simultaneously on different processes. Kernel code is preemptible. Your driver's code can lose the processor at any time, and the process that replaces it could also be running in your driver. Device interrupts asynchronous events that can cause concurrent execution of your code. The kernel also provides various mechanisms for delayed code execution, such as work queues, tasklets, and timers, which concurrency and its management 107. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 108 Friday, January 21st, 2005 10:41 am. Can cause your code to run at any time in ways unrelated to what the current process is doing. In the modern, hot pluggable world, your device could simply disappear while you are in the middle of working with it. Avoidance of race conditions can be an intimidating task. In a world where anything can happen at any time, how does a driver program avoid the creation of absolute chaos? As it turns out, most race conditions can be avoided through some thought, the kernel's concurrency control primitives, and the application of a few basic principles. We'll start with the principles first, then get into the specifics of how to apply them. Race conditions come about as a result of shared access to resources. When two threads of execution have a reason to work with the same data structures or hardware resources, the potential for mix-ups always exists. So the first rule of thumb to keep in mind as you design your driver is to avoid shared resources whenever possible. If there is no concurrent access, there can be no race conditions. So carefully written kernel code should have a minimum of sharing. The most obvious application of this idea is to avoid the use of global variables. If you put a resource in a place where more than one thread of execution can find it, there should be a strong reason for doing so. The fact of the matter is, however, that such sharing is often required. Hardware resources are, by their nature, shared, and software resources also must often be available to more than one thread. Bear in mind as well that global variables are far from the only way to share data. Anytime your code passes a pointer to some other part of the kernel, it is potentially creating a new sharing situation. Sharing is a fact of life. Here is the hard rule of resource sharing. Anytime that a hardware or software resources share beyond a single thread of execution, and the possibility exists that one thread could encounter an inconsistent view of that resource, you must explicitly manage access to that resource. In the Skull example above, process B's view of the situation is inconsistent, unaware that process A has already allocated memory for the shared device. It performs its own allocation and overwrites A's work. In this case, we must control access to the Skull data structure. We need to arrange things so that the code either sees memory that has been allocated or knows that no memory has been or will be allocated by anybody else. The usual technique for access management is called locking or mutual exclusion, making sure that only one thread of execution can manipulate a shared resource at any time. Much of the rest of this chapter will be devoted to locking. Asterisk for the purposes of this chapter. A thread of execution is any context that is running code. Each process is clearly a thread of execution, but so is an interrupt handler or other code running in response to an Asynchronous kernel event. 108 Chapter 5 Concurrency and Race Conditions. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 109 Friday, January 21st, 2005 10:41 am. First, however, we must briefly consider one other important rule. When kernel code creates an object that will be shared with any other part of the kernel, that object must continue to exist and function properly until it is known that no outside references to it exist. The instant that Skull makes its devices available, it must be prepared to handle requests on those devices, and Skull must continue to be able to handle requests on its devices until it knows that no reference, such as open user space files, to those devices exists. Two requirements come out of this rule. No object can be made available to the kernel until it is in a state where it can function properly, and references to such objects must be tracked. In most cases, you'll find that the kernel handles reference counting for you, but there are always exceptions. Following the above rules requires planning and careful attention to detail. It is easy to be surprised by concurrent access to resources you hadn't realized were shared. With some effort, however, most trace conditions can be headed off before they bite you or your users. Semaphores and mutexes. So let us look at how we can add locking to Skull. Our goal is to make our operations on the Skull data structure atomic, meaning that the entire operation happens at once, as far as other threads of execution are concerned. For our memory leak example, we need to ensure that if one thread finds that a particular chunk of memory must be allocated, it has the opportunity to perform that allocation before any other thread can make that test. To this end, we must set up critical sections, code that can be executed by only one thread at any given time. Not all critical sections are the same, so the kernel provides different primitives for different needs. In this case, every access to the Skull data structure happens in process context as a result of a direct user request. No accesses will be made from interrupt handlers or other asynchronous contexts. There are no particular latency, response time requirements. Application programmers understand that I/O requests are not usually satisfied immediately. Furthermore, the Skull is not holding any other critical system resource while it is accessing its own data structures. What all this means is that if the Skull driver goes to sleep while waiting for its turn to access the data structure, nobody is going to mind. Go to sleep is a well-defined term in this context. When a Linux process reaches a point where it cannot make any further processes, it goes to sleep, or locks, yielding the processor to somebody else until some future time when it can get work done again. Processors often sleep when waiting for I/O to complete. As we get deeper into the kernel, we will encounter a number of situations where we cannot sleep. The right method in Skull is not one of those situations, however, so we can use a locking mechanism that might cause the process to sleep while waiting for access to the critical section. Semaphores and mutexes. 109. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 110 Friday, January 21st, 2005 10:41 am. Just as importantly, we will be performing an operation, memory allocation with kmalloc, that could sleep. So sleeps are a possibility in any case. If our critical sections are to work properly, we must use a locking primitive that works when a thread that owns the lock sleeps. Not all locking mechanisms can be used where sleeping is a possibility. We'll see some that don't later in this chapter. For our present needs, however, The mechanism that fits best is a semaphore. Semaphores are a well-understood concept in computer science. At its core, a semaphore is a single integer value combined with a pair of functions that are typically called P and V. A process wishing to enter a critical section will call P on the relevant semaphore. If the semaphore's value is greater than 0, that value is decremented by 1 and the process continues. If, instead, the semaphore's value is 0 or less, the process must wait until somebody else releases the semaphore. Unlocking a semaphore is accomplished by calling V. This function increments the value of the semaphore and, if necessary, wakes up processes that are waiting. When semaphores are used for mutual exclusion, keeping multiple processes from running within a critical section simultaneously, their value will be initially set to 1. Such a semaphore can be held only by a single process or thread at any given time. A semaphore used in this mode is sometimes called a mutex, which is, of course, an abbreviation for mutual exclusion. Almost all semaphores found in the Linux kernel are used for mutual exclusion. The Linux semaphore implementation. The Linux kernel provides an implementation of semaphores that conforms to the above semantics. Although the terminology is a little different, to use semaphores, kernel code must include less than a semaphore greater than the relevant type as struct semaphore. Actual semaphores can be declared and initialized in a few ways. One is to create a semaphore directly, then set it up with sema_init, void sema_init, struct semaphore *same, int val, where val is the initial value to assign to a semaphore. Usually, however, semaphores are used in a mutex mode. To make this common case a little easier, the kernel has provided a set of helper functions and macros. Thus, a mutex can be declared and initialized with one of the following. Name. Here, the result is a semaphore variable called name that is initialized to 1. Width or 0. Width. In the latter case, the mutex starts out in a locked state. It will have to be explicitly unlocked before any thread will be allowed access. 110. Chapter 5 Concurrency and Race Conditions. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 111 Friday, January 21, 2005 10:41 am. If the mutex must be initialized at runtime, which is the case if it is allocated dynamically. For example, use one of the following. Void init mutex, struct semaphore *same, void init, struct semaphore *same. In the Linux world, the P function is called down, or some variation of that name. Here, down refers to the fact that the function decrements the value of the semaphore and, perhaps after putting the caller to sleep for a while to wait for the semaphore to become available, grants access to the protected resources. There are 3 versions of down. Void down, struct semaphore *same, int down_interruptible, struct semaphore *same, int down_trylock, struct semaphore *same. Down decrements the value of the semaphore and waits as long as need be. Down interruptible does the same, but the operation is interruptible. The interruptible version is almost always the one you will want. It allows a user space process that is waiting on a semaphore to be interrupted by the user. You do not, as a general rule, want to use non-interruptible operations unless there truly is no alternative. Non-interruptible operations are a good way to create unkillable processes. The dreaded D state seen in PS and annoy your users. Using down_interruptible requires some extra care. However, if the operation is interrupted, the function returns a non-zero value, and the caller does not hold the semaphore. Proper use of down_interruptible requires always checking the return value and responding accordingly. The final version, down_try_lock, never sleeps. If the semaphore is not available at the time of the call, down_try_lock returns immediately with a non-zero return value. Once a thread has successfully called one of the versions of down, it is said to be holding the semaphore, or to have taken out or acquired the semaphore. The thread is now entitled to access the critical section protected by the semaphore. When the operations requiring mutual exclusion are complete, the semaphore must be returned. The Linux equivalent to V is up, void up, struct semaphore asterisk same. Once up has been called, the caller no longer holds the semaphore. As you would expect, any thread that takes out a semaphore is required to release it. With one, and only one, call to up, special care is often required in error pods. If an error is encountered while a semaphore is held, that semaphore must be released before returning the error status to the caller. Failure to free a semaphore is an easy error to make. The result, processes hanging in seemingly unrelated places, can be hard to reproduce and track down. Semaphores in Mitexes 111. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 112 Friday, January 21st. 2005 10:41 am. Using semaphores in Skull. The semaphore mechanism gives Skull a tool that can be used to avoid race conditions while accessing the Skull_Dev data structure. But it is up to us to use that tool correctly. The keys to proper use of locking primitives are to specify exactly which resources are to be protected and to make sure that every access to those resources uses the proper locking. In our example driver, everything of interest is contained within the Skull_Dev structure. So that is the logical scope for our locking regime. Let's look again at that structure. Struct Skull_Dev, struct Skull_Q set asterisk data, asterisk pointer to first quantum set asterisk, int quantum, asterisk the current quantum size asterisk, int Q set, asterisk the current array size asterisk, unsigned long size, asterisk amount of data stored asterisk, unsigned int access_key, asterisk used by Skullout and Skullprev asterisk. Struct semaphore same, asterisk mutual exclusion semaphore asterisk, struct CDEV, asterisk char device structure asterisk, closing curly bracket. Toward the bottom of the structure is a member called same, which is, of course, our semaphore. We have chosen to use a separate semaphore for each virtual Skull device. It would have been equally correct to use a single global semaphore. The various Skull devices share no resources in common, however, and there is no reason to make one process wait while another process is working with a different Skull device. Using a separate semaphore for each device allows operations on different devices to proceed in parallel and, therefore, improves performance. Semaphores must be initialized before use. Skull performs this initialization at load time in this loop. For I equals 0, I less than Skull_nr_devs, I plus plus, opening curly bracket, Skull_devices, I, quantum equals Skull_quantum, Skull_devices, I, qset equals Skull_qset, init mutex, and Skull_devices, I, dot same, Skull_setup_cdev, and Skull_devices, I, closing curly bracket. Note that the semaphore must be initialized before the Skull device is made available to the rest of the system. Therefore, init_mutex is called before Skull_setup_cdev. Performing these operations in the opposite order would create a race condition, where the semaphore could be accessed before it is ready. Next, we must go through the code and make sure that no access is to the Skull_Dev data structure are made without holding the semaphore. Thus, for example, skull_right begins with this code. If down_interruptible and they've to same, return ERESTARTSYS. 112 Chapter 5 Concurrency and Race Conditions. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 113 Friday, January 21, 2005 10:41 am. Note the check on the return value of down_interruptible. If it returns non-zero, the operation was interrupted. The usual thing to do in this situation is to return ERESTARTSYS. Upon seeing this return code, the higher layers of the kernel will either restart the call from the beginning or return the error to the user. If you return ERESTARTSYS, you must first undo any user visible changes that might have been made, so that the right thing happens when the system call is retried. If you cannot undo things in this manner, you should return EINTR instead. Skull_right must release the semaphore whether or not it was able to carry out its other tasks successfully. If all goes well, execution falls into the final few lines of the function out, up, and they've to same, return retval. This code frees the semaphore and returns whatever status is called for. There are several places in skull_right where things can go wrong. These include memory allocation failures or a fault while trying to copy data from user space. In those cases, the code performs a go to out, ensuring that the proper cleanup is done. Reader-writer semaphores. Semaphores perform mutual exclusion for all callers, regardless of what each thread may want to do. Many tasks break down into two distinct types of work. However, tasks that only need to read the protected data structures and those that must make changes. It is often possible to allow multiple concurrent readers, as long as nobody is trying to make any changes. Doing so can optimize performance significantly. Read-only tasks can get their work done in parallel without having to wait for other readers to exit the critical section. The Linux kernel provides a special type of semaphore called RWSEM, or reader-writer semaphore. For this situation, the use of RWSEMs in drivers is relatively rare, but they are occasionally useful. Code using RWSEMs must include less than Linux RWSEM h greater than the relevant data type for reader-writer semaphores is struct RW_semaphore. An RWSEM must be explicitly initialized at runtime with void init_RWSEM. Struct RW_semaphore *same. A newly initialized RWSEM is available for the next task, reader or writer, that comes along. The interface for code needing read-only access is void down_read. Struct RW_semaphore *same. Int down_read_try_lock. Struct RW_semaphore *same. Void up_read. Struct RW_semaphore *same. A call to down_read provides read-only access to the protected resources, possibly concurrently with other readers. Note that down_read may put the calling process semaphores in mid-access 113. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 114 Friday, January 21, 2005 10:41 am. Into an uninterruptible sleep. Down_read_try_lock will not wait if read access is unavailable. It returns non-zero if access was granted, zero otherwise. Note that the convention for down_read_try_lock differs from that of most kernel functions. where success is indicated by a return value of 0. RWSEM obtained with down_red must eventually be freed with up_red. The interface for writers is similar. Void down_right. Struct RW_semaphore same. In the down_right_trilog. Struct RW_semaphore same. Void up_right. Struct RW_semaphore same. Void downgrade_right. Struct RW_semaphore same. Down_right. Down_right_trilog. And up_right all behave just like their read counterparts. Except, of course, that they provide write access. If you have a situation where a write lock is needed for a quick change, followed by a longer period of read-only access, you can use downgrade_right to allow other readers in once you have finished making changes. An RWSEM allows either one writer or an unlimited number of readers to hold the semaphore. Writers get priority as soon as a writer tries to enter the critical section. No readers will be allowed in until all writers have completed their work. This implementation can lead to reader starvation, where readers are denied access for a long time. If you have a large number of writers contending for the semaphore. For this reason, RWSEMs are best used when write access is required only rarely, and writer access is held for short periods of time. Completions. A common pattern in kernel programming involves initiating some activity outside of the current thread, then waiting for that activity to complete. This activity can be the creation of a new kernel thread or user space process, a request to an existing process, or some sort of hardware-based action. In such cases, it can be tempting to use a semaphore for synchronization of the two tasks, with code such as struct semaphore same, init, and same, start_external_task, and same, down, and same. The external task can then call up, and same, when its work is done. As it turns out, semaphores are not the best tool to use in this situation. In normal use, code attempting to lock a semaphore finds that semaphore available almost all the time. If there is significant contention for the semaphore, performance suffers and the locking scheme needs to be reviewed. So semaphores have been heavily optimized for the available case, when used to communicate task completion in the way shown above. However, the thread calling down will almost always have to wait. Performance 114, Chapter 5, Concurrency and Race Conditions. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 115 Friday, January 21, 2005 10:41 am. Will suffer accordingly. Semaphores can also be subject to a difficult race condition. When used in this way, if they are declared as automatic variables. In some cases, the semaphore could vanish before the process calling up is finished with it. These concerns inspired the addition of the completion interface in the 2.4.7 kernel. Completions are a lightweight mechanism with one task, allowing one thread to tell another that the job is done. To use completions, your code must include less than Linux completion h greater than. A completion can be created with my_completion, or, if the completion must be created and initialized dynamically, struct completion my_completion, init_completion, and my_completion. Waiting for the completion is a simple matter of calling void wait_for_completion, struct completion *c. Note that this function performs an uninterruptible wait. If your code calls wait_for completion and nobody ever completes the task, the result will be an unkillable process *. On the other side, The actual completion event may be signaled by calling one of the following: void complete, struct completion *c, void complete _all, struct completion *c. The two functions behave differently if more than one thread is waiting for the same completion event. Complete wecks up only one of the waiting threads, while complete _all allows all of them to proceed. In most cases, there is only one waiter, and the two functions will produce an identical result. A completion is normally a one-shot device. It is used once then discarded. It is permissible, however, to reuse completion structures if proper care is taken. If complete _all is not used, a completion structure can be reused without any problems as long as there is no ambiguity about what event is being signaled. If you use complete _all, however, you must reinitialize the completion structure before reusing it. The macro struct completion C can be used to quickly perform this reinitialization. As an example of how completions may be used, consider the complete module, which is included in the example source. This module defines a device with simple semantics. Any process trying to read from the device will wait, using wait _for _completion. Asterisk as of this writing. Patches adding interruptible versions were in circulation but had not been merged into the mainline. Completions 115. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 116 Friday, January 21st, 2005 10:41 am. Until some other process writes to the device. The code which implements this behavior is comp s size _t complete _read struct file *filp char _user *buf size _t count lof _t *pos opening curly bracket print k process %i %s going to sleep n current come wait _for _completion and comp print k awoken %i %s n current come return 0 *of closing curly bracket s size _t complete _write struct file *filp const char _user *buf size _t count lof _t *pos opening curly bracket print k process %i %s awakening the readers n current come complete and comp return count succeed. To avoid retrial closing curly bracket. It is possible to have multiple processors reading from this device at the same time. Each write to the device will cause exactly one read operation to complete. But there is no way to know which one it will be. A typical use of the completion mechanism is with kernel thread termination at mod exit time. In the prototypical case, some of the driver internal workings is performed by a kernel thread in a while 1 loop. When the module is ready to be cleaned up, the exit function tells the thread to exit and then waits for completion. To the same, the kernel includes a specific function to be used by the thread. Void complete _and _exit struct completion *c long ritual spin locks. Semaphores are a useful tool for mutual exclusion, but they are not the only such tool provided by the kernel. Instead, most locking is implemented with a mechanism called a spin lock. Unlike semaphores, spin locks may be used in code that cannot sleep, such as interrupt handlers. When properly used, spin locks offer higher performance than semaphores in general. They do, however, bring a different set of constraints on their use. Spin locks are simple in concept. A spin lock is a mutual exclusion device that can have only two values, locked and unlocked. It is usually implemented as a single bit in an integer value. Code wishing to take out a particular lock tests the relevant bit. If the lock is available, the locked bit is set and the code continues into the critical section. If, instead, the lock has been taken by somebody else, the code goes into 116, Chapter 5, Concurrency and Race Conditions. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 117 Friday, January 21st, 2005 10:41 am. A tight loop where it repeatedly checks the lock until it becomes available. This loop is the spin part of a spin lock. Of course, the real implementation of a spin lock is a bit more complex than the description above. The test and set operation must be done in an atomic manner, so that only one thread can obtain the lock, even if several are spinning at any given time. Care must also be taken to avoid deadlocks on hyper-threaded processors, chips that implement multiple virtual CPUs sharing a single processor core in cache. So the actual spin lock implementation is different for every architecture that Linux supports. The core concept is the same on all systems. However, when there is contention for a spin lock, the processes that are waiting execute a tight loop and accomplish no useful work. Spin locks are, by their nature, intended for use on multiprocessor systems. Although a uniprocessor workstation running a preemptive kernel behaves like SMP. As far as concurrency is concerned, if a non-preemptive uniprocessor system ever went into a spin on a lock, it would spin forever. No other thread would ever be able to obtain the CPU to release the lock. For this reason, spin lock operations on uniprocessor systems without preemption enabled are optimized to do nothing, with the exception of the ones that change the ARQ masking status because of preemption. Even if you never expect your code to run on an SMP system, you still need to implement proper locking. Introduction to the spin lock API. The required include file for the spin lock primitives is less than Linux spin lock h greater than. An actual lock has the type spin lock _t. Like any other data structure, a spin lock must be initialized. This initialization may be done at compile time as follows: spin lock _t my_lock equals, or at runtime with void spin _lock _init. Spin lock _t asterisk lock. Before entering a critical section, your code must obtain the requisite lock with void spin _lock. Spin lock _t asterisk lock. Note that all spin lock waits are, by their nature, uninterruptible. Once you call spin _lock, you will spin until the lock becomes available. To release a lock that you have obtained, pass it to void spin _unlock. Spin lock _t asterisk lock. There are many other spin lock functions, and we will look at them all shortly. But none of them depart from the core idea shown by the functions listed above. There is very little that one can do with the lock, other than lock and release it. However, there. Spin locks 117. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 118 Friday, January 21st, 2005 10:41 am. Are a few rules about how you must work with spin locks. We will take a moment to look at those before getting into the full spin lock interface. Spin locks in atomic context. Imagine for a moment that your driver acquires a spin lock and goes about its busyness within its critical section. Somewhere in the middle, your driver loses the processor. Perhaps it has called a function, copy _from _user, say, that puts the process to sleep. Or, perhaps, kernel preemption kicks in, and a higher priority process pushes your code aside. Your code is now holding a lock that it will not release any time in the foreseeable future. If some other thread tries to obtain the same lock, it will, in the best case, wait, spinning in the processor, for a very long time. In the worst case, the system could deadlock entirely. Most readers would agree that this scenario is best avoided. Therefore, the core rule that applies to spin locks is that any code must, while holding a spin lock, be atomic. It cannot sleep. In fact, it cannot relinquish the processor for any reason except to service interrupts, and sometimes not even then. The kernel preemption case is handled by the spin lock code itself. Anytime kernel code holds a spin lock, preemption is disabled on the relevant processor. Even uniprocessor systems must disable preemption in this way to avoid race conditions. That is why proper locking is required even if you never expect your code to run on a multiprocessor machine. Avoiding sleep while holding a lock can be more difficult. Many kernel functions can sleep, and this behavior is not always well documented. Copying data to or from user space is an obvious example. The required user space page may need to be swapped in from the disk before the copy can proceed, and that operation clearly requires a sleep. Just about any operation that must allocate memory can sleep. Malloc can decide to give up the processor and wait for more memory to become available, unless it is explicitly told not to. Sleeps can happen in surprising places. Writing code that will execute under a spin lock requires paying attention to every function that you call. Here's another scenario. Your driver is executing and has just taken out a lock that controls access to its device. While the lock is held, the device issues an interrupt, which causes your interrupt handler to run. The interrupt handler, before accessing the device, must also obtain the lock. Taking out a spin lock in an interrupt handler is a legitimate thing to do. That is one of the reasons that spin lock operations do not sleep. But what happens if the interrupt routine executes in the same processor as the code that took out the lock originally? While the interrupt handler is spinning, the non-interrupt code will not be able to run to release the lock. That processor will spin forever. 118. Chapter 5 Concurrency and Race Conditions. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 119 Friday, January 21, 2005 10:41 am. Avoiding this trap requires disabling interrupts on the local CPU only. While the spin lock is held, there are variants of the spin lock functions that will disable interrupts for you. We'll see them in the next section. However, a complete discussion of interrupts must wait until Chapter 10. The last important rule for spin lock usage is that spin locks must always be held for the minimum time possible. The longer you hold a lock, the longer another processor may have to spin waiting for you to release it, and the chance of it having to spin at all is greater. Long lock hold times also keep the current processor from scheduling, meaning that a higher priority process, which really should be able to get the CPU, may have to wait. The kernel developers put a great deal of effort into reducing kernel latency. The time a process may have to wait to be scheduled. In the 2.5 development series, a poorly written driver can wipe out all that progress just by holding a lock for too long. To avoid creating this sort of problem, make a point of keeping your lock hold times short. The spin lock functions. We have already seen two functions, spin_lock and spin_unlock, that manipulate spin locks. There are several other functions, however, with similar names and purposes. We will now present the full set. This discussion will take us into ground we will not be able to cover properly for a few chapters yet. A complete understanding of this spin lock AP requires an understanding of interrupt handling and related concepts. There are actually 4 functions that can lock a spin lock: void spin underscore lock, spin lock underscore T asterisk lock, void spin underscore lock underscore IRQ save, spin lock underscore T asterisk lock, unsigned long flags, void spin underscore lock underscore IRQ, spin lock underscore T asterisk lock, void spin underscore lock underscore BH, spin lock underscore T asterisk lock. We have already seen how spin underscore lock works. Spin underscore lock underscore IRQ save disables interrupts on the local processor only before taking the spin lock. The previous interrupt state is stored in flags. If you are absolutely sure nothing else might have already disabled interrupts on your processor, or, in other words, you are sure that you should enable interrupts when you release your spin lock, you can use spin underscore lock underscore IRQ instead and not have to keep track of the flags. Finally, spin underscore lock underscore BH disables software interrupts before taking the lock, but leaves hardware interrupts enabled. If you have a spin lock that can be taken by code that runs in hardware or software interrupt context, you must use one of the forms of spin underscore lock that disables interrupts. Doing otherwise can deadlock the system sooner or later. If you do not access your lock in a hardware interrupt handler, but you do via software interrupts in code that runs out of a tasklet, for example, a topic covered in Chapter 7, you can use spin underscore lock underscore BH to safely avoid deadlocks while still allowing hardware interrupts to be serviced. Spin Locks 119. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 120 Friday, January 21st, 2005 10:41 am. There are also 4 ways to release a spin lock. The one you use must correspond to the function you use to take the lock. Void spin underscore unlock, spin lock underscore T asterisk lock, void spin underscore unlock underscore IRQ restore, spin lock underscore T asterisk lock, unsigned long flags, void spin underscore unlock underscore IRQ, spin lock underscore T asterisk lock, void spin underscore unlock underscore BH, spin lock underscore T asterisk lock. Each spin underscore unlock variant enters the work performed by the corresponding spin underscore lock function. The flags argument passed to spin underscore unlock underscore IRQ restore must be the same variable passed to spin underscore lock underscore IRQ save. You must also call spin underscore lock underscore IRQ save and spin unlock underscore IRQ restore in the same function. Otherwise, your code may break on some architectures. There is also a set of non-blocking spin lock operations. Int spin underscore try lock, spin lock underscore T asterisk lock, int spin underscore try lock underscore BH, spin lock underscore T asterisk lock. These functions return non-zero or on success. The lock was obtained. 0 otherwise. There is no try version that disables interrupts. Reader-writer spin locks. The kernel provides a reader-writer form of spin locks that is directly analogous to the reader-writer semaphores we saw earlier in this chapter. These locks allow any number of readers into a critical section simultaneously, but writers must have exclusive access. Reader-writer locks have a type of RW lock underscore T defined in less than Linux spin lock h greater than. They can be declared and initialized in 2 ways. RW lock underscore T my underscore RW lock equals asterisk static v asterisk RW lock underscore T my underscore RW lock RW lock underscore init and my underscore RW lock asterisk dynamic v asterisk. The list of functions available should look reasonably familiar by now. For readers, the following functions are available. void read underscore lock, rw lock underscore t asterisk lock, void read underscore lock underscore irq save, rw lock underscore t asterisk lock, unsigned long flags, void read underscore lock underscore irq, rw lock underscore t asterisk lock, void read underscore lock underscore bh, rw lock underscore t asterisk lock, void read underscore unlock, rw lock underscore t asterisk lock, void read underscore unlock underscore irq restore, rw lock underscore t asterisk lock, unsigned long flags, void read underscore unlock underscore irq, rw lock underscore t asterisk lock, void read underscore unlock underscore bh, rw lock underscore t asterisk lock. Interestingly, there is no read underscore try lock. The functions for write access are similar. Void write underscore lock, rw lock underscore t asterisk lock, void write underscore lock underscore irq save, rw lock underscore t asterisk lock, unsigned long flags. 120. Chapter 5 Concurrency and Race Conditions. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 121 Friday, January 21st, 2005 10:41 am. Void write underscore lock underscore irq, rw lock underscore t asterisk lock, void write underscore lock underscore bh, rw lock underscore t asterisk lock, int write underscore try lock, rw lock underscore t asterisk lock, void write underscore unlock, rw lock underscore t asterisk lock, void write underscore unlock underscore irq restore, rw lock underscore t asterisk lock, unsigned long flags, void write underscore unlock underscore irq, rw lock underscore t asterisk lock, void write underscore unlock underscore bh, rw lock underscore t asterisk lock. Reader writer locks can starve readers just as RWSEMS can. This behavior is really a problem. However, if there is enough lock contention to bring about starvation, performance is poor anyway. Locking traps. Many years of experience with locks, experience that predates Linux, have shown that locking can be very hard to get right. Managing concurrency is an inherently tricky undertaking, and there are many ways of making mistakes. In this section, we take a quick look at things that can go wrong. Ambiguous rules. As has already been said above, a proper locking scheme requires clear and explicit rules. When you create a resource that can be accessed concurrently, you should define which lock will control that access. Locking should really be laid out at the beginning. It can be a hard thing to retrofit in afterward. Time taken at the outset usually is paid back generously at debugging time. As you write your code, you will doubtless encounter several functions that all require access to structures protected by a specific lock. At this point, you must be careful. If one function acquires a lock and then calls another function that also attempts to acquire the lock, your code deadlocks. Neither semaphores nor spin locks allow a lock holder to acquire the lock a second time. Should you attempt to do so, things simply hang. To make your locking work properly, you have to write some functions with the assumption that their caller has already acquired the relevant lock. Usually, only your internal static functions can be written in this way. Functions called from outside must handle locking explicitly. When you write internal functions that make assumptions about locking, do yourself and anybody else who works with your code a favor and document those assumptions explicitly. It can be very hard to come back months later and figure out whether you need to hold a lock to call a particular function or not. In the case of Skull, the design decision taken was to require all functions invoked directly from system calls to acquire the semaphore applying to the device structure. Locking Traps 121. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 122 Friday, January 21st, 2005 10:41 am. That is accessed. All internal functions, which are only called from other skull functions, can then assume that the semaphore has been properly acquired. Lock ordering rules. In systems with a large number of locks, and the kernel is becoming such a system, it is not unusual for code to need to hold more than one lock at once. If some sort of computation must be performed using two different resources, each of which has its own lock, there is often no alternative to acquiring both locks. Taking multiple locks can be dangerous. However, if you have two locks, called Lock 1 and Lock 2, and code needs to acquire both at the same time, you have a potential deadlock. Just imagine one thread locking Lock 1 while another simultaneously takes Lock 2. Then each thread tries to get the one it doesn't have. Both threads will deadlock. The solution to this problem is usually simple. When multiple locks must be acquired, they should always be acquired in the same order. As long as this convention is followed, simple deadlocks like the one described above can be avoided. However, following lock ordering rules can be easier said than done. It is very rare that such rules are actually written down anywhere. Often the best you can do is to see what other code does. A couple of rules of thumb can help. If you must obtain a lock that is local to your code, a device lock, say, along with a lock belonging to a more central part of the kernel, take your lock first. If you have a combination of semaphores and spin locks, you must, of course, obtain the semaphore S first. Calling down, which can sleep while holding a spin lock, is a serious error. But most of all, try to avoid situations where you need more than one lock. Fine versus coarse-grained locking. The first Linux kernel that supported multiprocessor systems was 2.0. It contained exactly one spin lock. The big kernel lock turned the entire kernel into one large critical section. Only one CPU could be executing kernel code at any given time. This lock solved the concurrency problem well enough to allow the kernel developers to address all of the other issues involved in supporting SMP. But it did not scale very well. Even a two-processor system could spend a significant amount of time simply waiting for the big kernel lock. The performance of a four-processor system was not even close to that of four independent machines. So, subsequent kernel releases have included fine-grained locking. In 2.2, one spin lock controlled access to the block I/O subsystem. Another worked for networking, and so on. A modern kernel can contain thousands of locks, each protecting one small resource. This sort of fine-grained locking can be good for scalability. It allows 122 Chapter 5 concurrency and race conditions. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 123 Friday, January 21st, 2005 10:41 am. Each processor to work on its specific task without contending for locks used by other processors. Very few people miss the big kernel lock asterisk. Fine-grained locking comes at a cost. However, in a kernel with thousands of locks, it can be very hard to know which locks you need, and in which order you should acquire them to perform a specific operation. Remember that locking bugs can be very difficult to find. More locks provide more opportunities for truly nasty locking bugs to creep into the kernel. Fine-grained locking can bring a level of complexity that, over the long term, can have a large adverse effect on the maintainability of the kernel. Locking in a device driver is usually relatively straightforward. You can have a single lock that covers everything you do. Or you can create one lock for every device you manage. As a general rule, you should start with relatively cost locking unless you have a real reason to believe that contention could be a problem. Resist the urge to optimize prematurely. The real performance constraints often show up in unexpected places. If you do suspect that lock contention is hurting performance, you may find the lock meter tool useful. This patch, available at http://os.sgi.com/projects/lockmeter/ instruments the kernel to measure time spent vetting in locks. By looking at the report, you are able to determine quickly whether lock contention is truly the problem or not. Alternatives to locking. The Linux kernel provides a number of powerful locking primitives that can be used to keep the kernel from tripping over its own feet. But, as we have seen, the design and implementation of a locking scheme is not without its pitfalls. Often there is no alternative to semaphores and spin locks. They may be the only way to get the job done properly. There are situations, however, where atomic access can be set up without the need for full locking. This section looks at other ways of doing things. Lock-free algorithms. Sometimes, you can recast your algorithms to avoid the need for locking altogether. A number of reader-writer situations, if there is only one writer, can often work in this manner. If the writer takes care that the view of the data structure, as seen by the reader, is always consistent, it may be possible to create a lock-free data structure. A data structure that can often be useful for lockless producer-consumer tasks is the circular buffer. This algorithm involves a producer placing data into one end of an asterisk. This lock still exists in 2.6, though it covers very little of the kernel now. If you stumble across a lock_kernel call, you have found the big kernel lock. Do not even think about using it in any new code. However, alternatives to locking. 123. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly & Associates, Inc. All rights reserved. ch05.7955 page 124 Friday, January 21, 2005 10:41 am. Array. While the consumer removes data from the other, when the end of the array is reached, the producer wraps back around to the beginning. So a circular buffer requires an array and to index values to track where the next new value goes and which value should be removed from the buffer next. When carefully implemented, a circular buffer requires no locking in the absence of multiple producers or consumers. The producer is the only thread that is allowed to modify the write index in the array location it points to. As long as the writer stores a new value into the buffer before updating the write index, the reader will always see a consistent view. The reader, in turn, is the only thread that can access the read index in the value it points to, with a bit of care to ensure that the two pointers do not overrun each other. The producer and the consumer can access the buffer concurrently with no race conditions. Figure 5:1 shows circular buffer in several states of fill. This buffer has been defined such that an empty condition is indicated by the read and write pointers being equal, while a full condition happens whenever the write pointer is immediately behind the read pointer. Being careful to account for a wrap when carefully programmed, this buffer can be used without locks. Write, read, write, read, write, circular buffer, full buffer, empty buffer. Figure 5:1. A circular buffer. Circular buffers show up reasonably often in device drivers. Networking adapters, in particular, often use circular buffers to exchange data packets with the processor. Note that, as of 2.6.10, there is a generic circular buffer implementation available in the kernel. See less than Linux ch05 greater than for information on how to use it. Atomic variables. Sometimes, A shared resource is a simple integer value. Suppose your driver maintains a shared variable n_op that tells how many device operations are currently outstanding. Normally, even a simple operation such as n_op ++ 124, Chapter 5, Concurrency and Race Conditions. This is the title of the book. E-Matter Edition. Copyright 2005, O'Reilly and Associates, Inc. All rights reserved. ch05.7955, page 125, Friday, January 21, 2005, 10:41 am. Would require locking. Some processes might perform that sort of increment in an atomic manner, but you can't count on it. But a full locking regime seems like overhead for a simple integer value. For cases like this, the kernel provides an atomic integer type called atomic_t, defined in less than ASM. Atomic h greater than an atomic_t holds an int value on all supported architectures. Because of the way this type works on some processes, however, the full integer range may not be available. Thus, you should not count on an atomic_t holding more than 24 bits. The following operations are defined for the type and are guaranteed to be atomic. With respect to all processes of an SMP computer, the operations are very fast, because they compile to a single machine instruction whenever possible. Void atomic_set, atomic_t *v, int I, atomic_t v equals 0. Set the atomic variable v to the integer value I. You can also initialize atomic value s at compile time with the macro int atomic_red, atomic_t *v. Return the current value of v. Void atomic_add, int I, atomic_t *v. Add I to the atomic variable pointed to by v. The return value is void, because there is an extra cost to returning the new value, and most of the time there's no need to know it. Void atomic_sub, int I, atomic_t *v. Subtract I from *v. Void atomic_inc, atomic_t *v. Void atomic_dec, atomic_t *v. Increment or decrement an atomic variable. Int atomic_inc_n_test, atomic_t *v. Int atomic_dec_n_test, atomic_t *v. Int atomic_sub_n_test, int I, atomic_t *v. Perform the specified operation and test the result. If, after the operation, the atomic value is 0, then the return value is true. Otherwise, it is false. Note that there is no atomic_add_n_test. Int atomic_add_negative. Int I, atomic_t *v. Add the integer variable I to v. The return value is true if the result is negative. False otherwise. Int atomic_add_return. Int I, atomic_t *v. Int atomic_sub_return. Int I, atomic_t *v. Int atomic_inc_return. Atomic_t *v. Int atomic_dec_return. Atomic_t *v. Behave just like atomic_add and friends, with the exception that they return the new value of the atomic variable to the caller. Alternatives to locking. 125. This is the title of the book. E-Matter Edition. Copyright 2005, O'Reilly and Associates, Inc. All rights reserved. ch05.7955, page 126, Friday, January 21, 2005, 10:41 am. As stated earlier, atomic_t data items must be accessed only through these functions. If you pass an atomic item to a function that expects an integer argument, you'll get a compiler error. You should also bear in mind that atomic_t values work only when the quantity in Question is truly atomic. Operations requiring multiple atomic _t variables still require some other sort of locking. Consider the following code: atomic _sub amount, and first atomic, atomic add amount, and second atomic. There is a period of time where the amount has been subtracted from the first atomic value but not yet added to the second. If that state of affairs could create trouble for code that might run between the two operations, some form of locking must be employed. Bit operations. The atomic _t type is good for performing integer arithmetic. It doesn't work as well, however, when you need to manipulate individual bits in an atomic manner. For that purpose, instead, the kernel offers a set of functions that modify or test single bits atomically. Because the whole operation happens in a single step, no interrupt or other processor can interfere. Atomic bit operations are very fast, since they perform the operation using a single machine instruction without disabling interrupts whenever the underlying platform can do that. The functions are architecture dependent and are declared in less than ASM bitlets h greater than. They are guaranteed to be atomic even on SMP computers and are useful to keep coherence across processes. Unfortunately, data typing in these functions is architecture dependent as well. The NR argument, describing which bit to manipulate, is usually defined as into bitters, and signed long for a few architectures. The address to be modified is usually a pointer to an assigned long, but a few architectures use void asterisk instead. The available bit operations are void set _bit, NR, void asterisk address, sets bit number NR in the data item pointed to by address, void clear _bit, NR, void asterisk address, clears the specified bit in the unsigned long datum that lives at address its sum in. Ticks are otherwise the same as set _bit, void change _bit, NR, void asterisk address, toggles the bit. 126 Chapter 5 Concurrency and Race Conditions. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 127 Friday, January 21st, 2005 10:41 am. Test _bit, NR, void asterisk address. This function is the only bit operation that doesn't need to be atomic. It simply returns the current value of the bit. Int test _in _set _bit, NR, void asterisk address. Int test _in _clear _bit, NR, void asterisk address. Int test _in _change _bit, NR, void asterisk address. Behave atomically like those listed previously, except that they also return the previous value of the bit. When these functions are used to access and modify a shared flag, you don't have to do anything except call them. They perform their operations in an atomic manner, using bit operations to manage a lock variable that controls access to a shared variable. On the other hand, is a little more complicated and deserves an example. Most modern code does not use bit operations in this way, but code like the following still exists in the kernel. A code segment that needs to access a shared data item tries to atomically acquire lock using either test _in _set _bit or test _in _clear _bit. The usual implementation is shown here. It assumes that the lock lives at bit NR of address. It also assumes that the bit is 0 when the lock is free or non-zero when the lock is busy. Try to set lock asterisk, while test _in _set _bit, NR, address, equals 0. Wait for, while do your work asterisk release lock, in check, if test _in _clear _bit, NR, address, equals 0. Something underscore went underscore wrong. Asterisk already released. Error asterisk. If you read through the kernel source, you find code that works like this. For example, it is, however, far better to use spin locks in new code. Spin locks are well debugged. They handle issues like interrupts and kernel preemption. And others reading your code do not have to work to understand what you are doing. ch05. The 2.6 kernel contains a couple of new mechanisms that are intended to provide fast, lockless access to a shared resource. ch05 work in situations where the resource to be protected is small, simple, and frequently accessed, and where write access is rare but must be fast. Essentially, they work by allowing readers free access to the resource but requiring those readers to check for collisions with writers, and when such a collision happens, retry their access. ch05 generally cannot be used to protect data structures involving pointers, because the reader may be following a pointer that is invalid while the writer is changing the data structure. Alternatives to locking. 127. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly & Associates, Inc. All rights reserved. ch05.7955 page 128 Friday, January 21, 2005 10:41 am. ch05 are defined in less than Linux. ch05 h greater than. There are the two usual methods for initializing a ch05, which has type ch05_t. ch05_t lock1 equals ch05_t lock2. ch05_init and lock2. Read access works by obtaining an unsigned integer sequence value on entry into the critical section. On exit, that sequence value is compared with the current value. If there is a mismatch, the read access must be retried. As a result, reader code has a form like the following: unsigned ch do ch equals read underscore ch beginning and the underscore lock asterisk do what you need to do asterisk while read underscore secretary and the underscore lock suck. This sort of lock is usually used to protect some sort of simple computation that requires multiple consistent values. If the test at the end of the computation shows that a concurrent write occurred, the results can be simply discarded and recomputed. If your ch05 might be accessed from an interrupt handler, you should use the IRQ safe versions instead. Unsigned read underscore ch beginning underscore IRQ save. ch05_t asterisk lock. Unsigned long flags. Read underscore secretary underscore IRQ restore. ch05_t asterisk lock. Unsigned ch. Unsigned long flags. Writers must obtain an exclusive lock to enter the critical section protected by a ch05. To do so, call void write underscore ch05. ch05_t asterisk lock. The write lock is implemented with spin lock, so all the usual constraints apply. Make a call to void write underscore second lock. ch05_t asterisk lock to release the lock. Since spin locks are used to control write access, all of the usual variants are available. Void write underscore ch05 underscore IRQ save. ch05_t asterisk lock. Unsigned long flags. Void write underscore ch05 underscore IRQ. ch05_t asterisk lock. Void write underscore ch05 underscore bh. ch05_t asterisk lock. Void write underscore second lock underscore IRQ restore. ch05_t asterisk lock. Unsigned long flags. Void write underscore second lock underscore IRQ. ch05_t asterisk lock. Void write underscore second lock underscore bh. ch05_t asterisk lock. There is also a write underscore tree ch05 that returns non-zero if it was able to obtain the lock. 128 Chapter 5 Concurrency and Race Conditions. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly & Associates, Inc. All rights reserved. ch05.7955 page 129 Friday, January 21st, 2005 10:41 am. Read copy update. Read copy update. RCU is an advanced mutual exclusion scheme that can yield high performance in the right conditions. Its use in drivers is rare but not unknown, so it is worth a quick overview here. Those who are interested in the full details of the RCU algorithm can find them in the white paper published by its creator. http://www.rdrop.com/user/box/clock/intro/clock_intro.html. RCU places a number of constraints on the sort of data structure that it can protect. It is optimized for situations where reads are common and writes are rare. The resources being protected should be accessed via pointers, and all references to those resources must be held only by atomic code. When the data structure needs to be changed, the writing thread makes a copy, changes the copy, then aims the relevant pointer at the new version. Thus, the name of the algorithm. When the kernel is sure that no references to the old version remain, it can be freed. As an example of real-world use of RCU, consider the network routing tables. Every outgoing packet requires a check of the routing tables to determine which interface should be used. The check is fast, and once the kernel has found the target interface, it no longer needs the routing table entry. RCU allows route lookups to be performed without locking, with significant performance benefits. The star mode radio IP driver in the kernel also uses RCU to keep track of its list of devices. Code using RCU should include less than Linux RC update h greater than. On the read side, code using an RCU protected data structure should bracket its references with calls to RCU_read_lock and RCU_read_unlock. As a result, RCU code tends to look like struct my_stuff *stuff RCU_read_lock stuff equals find_the_stuff args do_something_with stuff RCU_read_unlock. The RCU_read_lock call is fast. It disables kernel preemption but does not wait for anything. The code that executes while the read lock is held must be atomic. No reference to the protected resource may be used after the call to RCU_read_unlock. Code that needs to change the protected structure has to carry out a few steps. The first part is easy. It allocates a new structure, copies data from the old one if need be, then replaces the pointer that is seen by the read code. At this point, for the purposes of the read side, the change is complete. Any code entering the critical section sees the new version of the data. All that remains is to free the old version. The problem, of course, is that code running on other processes may still have a reference to the older data, so it cannot be freed immediately. Instead, the write code must wait until it knows that no such reference. Alternatives to locking. 129. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 130 Friday, January 21st, 2005 10:41 am. Can exist since all code holding references to this data structure must, by the rules, be atomic. We know that once every processor on the system has been scheduled at least once, all references must be gone. So that is what RCU does. It sets aside a callback that waits until all processes have scheduled. That callback is then run to perform the cleanup work. Code that changes an RCU protected data structure must get its cleanup callback by allocating a struct RCU_head. Although it doesn't need to initialize that structure in any way, Often, that structure is simply embedded within the larger resource that is protected by RCU. After the change to that resource is complete, a call should be made to void call _RCU. Struct RCU _head *head. Void *func. Void *arg. Void *arg. The given func is called when it is safe to free the resource. It is passed to the same arg that was passed to call _RCU. Usually, the only thing func needs to do is to call k-free. The full RCU interface is more complex than we have seen here. It includes, for example, utility functions for working with protected linked lists. See the relevant header files for the full story. Quick reference. This chapter has introduced a substantial set of symbols for the management of concurrency. The most important of these are summarized here. Hashtag include less than ASM semaphore h greater than. The include file that defines semaphores and the operations on them. Name. Two macros for declaring and initializing a semaphore used in mutual exclusion. Mode. Void init mutex. Struct semaphore *same. Void init. Struct semaphore *same. These two functions can be used to initialize a semaphore at runtime. Void down. Struct semaphore *same. In down _interruptible. Struct semaphore *same. In down _try-lock. Struct semaphore *same. Void up. Struct semaphore *same. Lock and unlock a semaphore. Down puts the calling process into an uninterruptible sleep if need be. Down _interruptible, instead, can be interrupted by a signal. Down _try-lock does not sleep. Instead, it returns immediately if the semaphore is unavailable. Code that locks a semaphore must eventually unlock it with up. 130 Chapter 5 Concurrency and Race Conditions. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 131 Friday, January 21, 2005 10:41 am. Struct rw_semaphore. Init _rwsem. Struct rw_semaphore *same. The reader-writer version of semaphores in the function that initializes it. Void down _red. Struct rw_semaphore *same. Int down _read _try-lock. Struct rw_semaphore *same. Void up _red. Struct rw_semaphore *same. Functions for obtaining and releasing read access to a read-writer semaphore. Void down _right. Struct rw_semaphore *same. Int down _right _try-lock. Struct rw_semaphore *same. Void up _right. Struct rw_semaphore *same. Void downgrade _right. Struct rw_semaphore *same. Functions for managing write access to a read-writer semaphore. Hashtag include less than Linux completion h greater than. Name. Init _completion. Struct completion *c. Struct completion c. The include file describing the Linux completion mechanism, and the normal methods for initializing completions should be used only to reinitialize a completion that has been previously used. Void wait _for completion. Struct completion *c. Wait for a completion event to be signaled. Void complete. Struct completion *c. Void complete _all. Struct completion *c. Signal a completion event. Complete wakes at most one waiting thread, while complete _all wakes all waiters. Void complete _ and _exit. Struct completion *c. Long ritual signals a completion event by calling complete and calls exit for the current thread. Hashtag include less than Linux spinlock h greater than. Spinlock _t lock equals spin underscore lock underscore init, spin lock underscore t asterisk lock. The include file defining the spin lock interface and the two ways of initializing locks. Void spin underscore lock, spin lock underscore t asterisk lock. Void spin underscore lock underscore arq save, spin lock underscore t asterisk lock. Unsigned long flags. Void spin underscore lock underscore arq, spin lock underscore t asterisk lock. Void spin underscore lock underscore bh, spin lock underscore t asterisk lock. The various ways of locking a spin lock in. Possibly disabling interrupts. Quick reference 131. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 132 Friday, January 21st, 2005 10:41 am. Int spin underscore try lock, spin lock underscore t asterisk lock. Int spin underscore try lock underscore bh, spin lock underscore t asterisk lock. Non-spinning versions of the above functions. These return 0 in case of failure to obtain the lock, non-zero otherwise. Void spin underscore unlock, spin lock underscore t asterisk lock. Void spin underscore unlock underscore arq restore, spin lock underscore t asterisk lock. Unsigned long flags. Void spin underscore unlock underscore arq, spin lock underscore t asterisk lock. Void spin underscore unlock underscore bh, spin lock underscore t asterisk lock. The corresponding ways of releasing a spin lock. RW lock underscore t lock equals RW lock underscore init, RW lock underscore t asterisk lock. The two ways of initializing reader-writer locks. Void reader underscore lock, RW lock underscore t asterisk lock. Void read underscore lock underscore arq save, RW lock underscore t asterisk lock. Unsigned long flags. Void read underscore lock underscore arq, RW lock underscore t asterisk lock. Void read underscore lock underscore bh, RW lock underscore t asterisk lock. Functions for obtaining read access to a reader-writer lock. Void read underscore unlock, RW lock underscore t asterisk lock. Void read underscore unlock underscore arq restore, RW lock underscore t asterisk lock. Unsigned long flags. Void read underscore unlock underscore arq, RW lock underscore t asterisk lock. Void read underscore unlock underscore bh, RW lock underscore t asterisk lock. Functions for releasing read access to a reader-writer spin lock. Void write underscore lock, RW lock underscore t asterisk lock. Void write underscore lock underscore arq save, RW lock underscore t asterisk lock. Unsigned long flags. Void write underscore lock underscore arq, RW lock underscore t asterisk lock. Void write underscore lock underscore bh, RW lock underscore t asterisk lock. Functions for obtaining write access to a reader-writer lock. Void write underscore unlock, RW lock underscore t asterisk lock. Void write underscore unlock underscore arq restore, RW lock underscore t asterisk lock. Unsigned long flags. Void write underscore unlock underscore arq, RW lock underscore t asterisk lock. Void write underscore unlock underscore bh, RW lock underscore t asterisk lock. Functions for releasing write access to a reader-writer spin lock. 132. Chapter 5 Concurrency and Race Conditions. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 133 Friday, January 21st, 2005 10:41 am. Hashtag include less than ASM atomic H greater than atomic underscore TV equals value. Void atomic underscore set atomic underscore T asterisk V. Int I. Int atomic underscore red atomic underscore T asterisk V, void atomic underscore add, int I, atomic underscore T asterisk V, void atomic underscore sub, int I, atomic underscore T asterisk V, void atomic underscore inc, atomic underscore T asterisk V, void atomic underscore dec, atomic underscore T asterisk V, int atomic underscore inc underscore and underscore test, atomic underscore T asterisk V, int atomic underscore dec underscore and underscore test, atomic underscore T asterisk V, int atomic underscore sub underscore and underscore test, int I, atomic underscore T asterisk V, int atomic underscore add underscore negative, int I, atomic underscore T asterisk V, int atomic underscore add underscore return, int I, atomic underscore T asterisk V, int atomic underscore sub underscore return, int I, atomic underscore T asterisk V, int atomic underscore inc underscore return, atomic underscore T asterisk V, int atomic underscore dec underscore return, atomic underscore T asterisk V, atomically access integer variables. The atomic underscore T variables must be accessed only through these functions. Hashtag include less than ASM bit ups h greater than void set underscore bit nr void asterisk address void clear underscore bit nr void asterisk address void change underscore bit nr void asterisk address test underscore bit nr void asterisk address int test underscore n underscore set underscore bit nr void asterisk address int test underscore n underscore clear underscore bit nr void asterisk address int test underscore n underscore change underscore bit nr void asterisk address atomically access bit values. They can be used for flags or lock variables. Using these functions prevents any race condition related to concurrent access to a bit. Hashtag include less than Linux suclock h greater than siclock underscore t lock equals siclock underscore init siclock underscore t asterisk lock. The include file defining siclocks in the two ways of initializing them. Unsigned int read underscore sicbeginning siclock underscore t asterisk lock. Unsigned int read underscore sicbeginning underscore irq save siclock underscore t asterisk lock. Unsigned long flags int read underscore secretary siclock underscore t asterisk lock. Unsigned int suck int read underscore secretary underscore irq restore siclock underscore t asterisk lock. Unsigned int suck. Unsigned long flags functions for obtaining read access to a siclock protected resources. Quick reference 133. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved. ch05.7955 page 134 Friday, January 21st, 2005 10:41 am. Void right underscore siclock. Siclock underscore t asterisk lock. Void right underscore siclock underscore irq save. Siclock underscore t asterisk lock. Unsigned long flags. Void right underscore siclock underscore irq. Siclock underscore t asterisk lock. Void right underscore siclock underscore bh. Siclock underscore t asterisk lock. Int right underscore tree siclock. Siclock underscore t asterisk lock. Functions for obtaining write access to a siclock protected resource. Void right underscore second lock. Siclock underscore t asterisk lock. Void right underscore second lock underscore irq restore. Siclock underscore t asterisk lock. Unsigned long flags. Void right underscore second lock underscore irq. Siclock underscore t asterisk lock. Void right underscore second lock underscore bh. Siclock underscore t asterisk lock. Functions for releasing write access to a siclock protected resource. Hashtag include less than Linux rc update h greater than. The include file required to use the read copy update RCU mechanism. Void RCU underscore read underscore lock. Void RCU underscore read underscore unlock. Macros for obtaining atomic read access to a resource protected by RCU. Void call _RCU. Struct RCU _head *head. Void *func. Void *arg. Void *arg. Arranges for a callback to run after all processes have been scheduled and an RCU protected resource can be safely freed. 134. Chapter 5 Concurrency and Race Conditions. This is the title of the book. E-Matter Edition. Copyright 2005 O'Reilly and Associates, Inc. All rights reserved.